Hello everyone. In this video, we'll be covering topics from the course Chemistry 1412, also known as General Chemistry 2. So I'm going to go ahead and share my screen, and we're going to look at a PowerPoint presentation that we're going to be covering for this video. As you can see, the two topics that we will be covering today is concentration terms and colligative properties. Listed below are the different concentration terms that you will actually need to know for the General Chemistry 2 course. The first one is molarity. It should be pretty familiar to you because you covered it in your General Chemistry 1 course. It's going to be represented with the capital letter M, and it's going to be moles of solute divided by volume of solution in liters. Molality is going to be a little m, and it's going to be moles of solute divided by kilograms of solvent. Parts by mass is a W divided by W, which is mass of solute divided by mass of solution. Parts by volume, V divided by V, is going to be volume of solute divided by volume of solution. And finally, we have mole fraction, which is an X, and it's going to be moles of solute divided by moles of solution. And just as a reminder that your solution is going to be your solvent plus your solute added together. So now we're going to go ahead and start to work through examples of each of our concentration terms. Our first one being molarity. They want to know how many grams of potassium carbonate are needed to make 200 milliliters of 2.5 molar solution. And we're given that potassium carbonate is K2CO3. But do be aware that on an exam, the formula, depending on your professor, might not always be provided. So because potassium is just one of the elements on the periodic table, you should know that it is a K, and carbonate is one of your polyatomic ions that are generally memorized during the Gen Chem 1 course. So do keep in mind that if you are rusty on your naming, that you go back and review those topics. So let me go ahead and write down what information we were given. So we have 200 milliliters and we have a 2.5 molar solution. So I'm going to go ahead and exit this and bring up the boogie board. So as you can see, I wrote down the information that was given, and we want to know grams of our solution. So I have a little G question mark because we don't know how many grams we have. To solve that, we can use the molarity equation. So molarity is capital M equals moles divided by liters. So we can set up with the information that we're given into our formula. So we had 2.5 molar solution equals moles divided by, we notice that it has to be in liters and we're given it in milliliters, so you have to convert your 200 milliliters to liters, which is going to be 0.2 liters. So we say 0.2 right here. We can, because it's dividing, we will multiply to get it to the other side. And we will get, so if we put moles as an X, because it's a variable we don't know, we can say that X equals 0.5 moles of K2CO3. So that's how many moles we have, but that's not really what we're looking for. We're looking for grams. So we'll have to do another conversion to get it from moles to grams. So we put 0.5 moles of K2CO3, And we can set it up on a reaction table to be able to do our conversion. So just like we do in General Chemistry 1, we can multiply or use the molar mass to be able to determine or convert our moles to grams. So our moles are up on top here, so they're going to go on bottom. So for every 1 mole of K2CO3, we have 138.2 grams of K2CO3. Our moles will cancel out, and we will get 69.1 grams of K2CO3. And this will be our answer. So for those that are a little rusty on your conversions, I got this number by simply adding all the weights from each of my compounds up. So I find the weight of K. I have 2 of them, so you have to add that twice, plus the weight of carbon, plus the weight of 3 oxygens, and you'll get the 138.2 grams. And that's how you solve a molarity type question. So now we're going to move back over to our PowerPoint so that we can see our next problem. We now have a molality question. So it says, calculate the molality of a solution prepared by dissolving. We have 45.38 grams of CdBr2 and 375 grams of water. So let's go back to our boogie board. As you can see, I wrote the information that we have, the 45.38 grams of CdBr2 and the 375 grams of water. So let's go ahead and write out the formula for molality. Remember, it's a little m, and it's going to be moles of solute divided by kilograms of solvent. And so the next part, hopefully it won't be too confusing, but you have to determine which one is your solvent and which one is your solute. So whenever you're dealing with water, it's generally going to be your solvent. It's going to be the thing that is dissolving. As another thing, in our notes we covered that your solvent is generally the more abundant component. So as you can see, we have 375 grams compared to the 45 grams of the CdBr2. So it's the more abundant component. So now we need to put each of our given compounds into its proper unit to plug into our problem. So we have moles of solute, but we're given it in grams. So we need to convert our 45.38 grams of CdBr2 into moles of CdBr2. So we say that 45.38 grams of CdBr2, we can set it up on a reaction table. So our grams are on top, which means our grams have to go down here on bottom. So for every 1 mole, we have 272.22 grams of CdBr2. Just like before, you get that number just by adding the weights of each compound or each element within our compound. Our grams will cancel out, and you multiply by what's on top, divide by what is on bottom, and you will get 0.1667 moles of CdBr2. Put a line here because this is what was given and this is the work that we have. So now we have our solute in its given form, or in the form that we need to plug into our equation. Now we need to convert our solvent into the kilograms from grams. So we have 375 grams of water. Grams are on top, so they have to be on bottom. So for every 1 kilogram, I have 1 times 10 to the third grams. This is just information that we learned back in General Chemistry 1, so converting from like kilo, micro, milli, that kind of thing. If you were not too familiar, I highly suggest looking it up so that you can know how to convert. If you have another way that you convert, you can use that as well. So our grams will cancel out, and we will get 0.375 kilograms of water. Now each of our components are in its proper form, and we can use those numbers to plug into our formula. So we say molality equals 0.1667 divided by 0.375. And this will equal 0.445 as our answer. All right, so let's go ahead and go back to our PowerPoint and move on to parts by mass. So we have a 4-gram sugar cube. So we have 4 grams of C12H22O11, which is known as sucrose, and is dissolved in a 350 milliliter cup or teacup of 80 degrees Celsius water. What is the percent composition by mass of the sugar solution? Given that the density of water at 80 degrees Celsius is 0.975 grams per milliliter. All right, so for this particular problem, we're solving for percent composition by mass, which is very similar to the parts by mass that we discussed earlier. However, there's one extra part for percent composition. Because we're dealing with the percent, we have to multiply by 100 after finding parts by mass. So as we can see here, to find the percent composition, it's going to be the mass of solute divided by mass of solution, which is the formula given for parts by mass, times 100. So let's go ahead and exit and go to our boogie board. So as you can see, this is the information that was given. So we have 4 grams of C12H22O11. We have a 350 milliliter teacup, and we know that the density for water is going to be 0.975 grams per milliliter. And we want to know the percent composition for that sugar solution. So we already know that our mass of our solute, so the thing being dissolved, is our 4 grams of the sucrose. Now we need to find our mass of our solution, but to do that, we have to find our mass of the solute, which is, or our solvent, sorry, which is our water. So to do that, we know that density equals mass divided by volume. And we need to find the mass given our density and our volume. So we can manipulate this equation to be able to solve for mass, to find the mass of the water. So we say mass equals density, which I'm just going to represent with a D, times volume, which I'm going to represent with a V. All I did is, because these were dividing originally, I have to multiply to get my volume to the other side, so density times volume equals mass. And I can plug in the information that I have to solve. So my mass equals 0.975 grams per milliliter times 350 milliliter container that we have, so the cup or the teacup. Our milliliters will cancel out, and this will give us a mass of 341.25 grams, and this is going to be the solvent, so the water. I can now add my mass of solvent to my mass of my solute to find the mass of the solution. So we say that our solution is 4 plus 341.25, and we'll get 345.25 grams as our solution. So now we can say percent composition equals 4 grams divided by the mass of the solute divided by the mass of the solution, so 345.25 grams times 100. When you do the math within the parentheses, you're going to get 0.0116 times 100. So our percent composition is going to be 1.16%, and that is the percent composition of sugar solution. So this is our answer. Right, let's go ahead and go back to our PowerPoint. All right, so now we have parts by volume. So this is going to be very similar to the last problem. However, instead of solving using mass, you're going to solve using volume. It's pretty simple too. So we have a solution is prepared by dissolving 90 milliliters of pure hydrogen peroxide and enough water to make a 3,000 milliliter solution. What is the concentration of hydrogen peroxide solution? So let's go ahead and go to our boogie board. So the volume percent is going to be set up the exact same way as our mass percent. So we say percent volume equals the volume of our solute divided by the volume of our solution times 100. So we say percent volume equals, they gave us our volume of solute and they also gave us our volume of solution. So all we have to do is plug it in. So we say the 90 milliliters divided by our 3,000 milliliters times 100. So when we do all of the math, we're going to get a volume percent of 3%. And that's all you have to do. So a lot of times you'll end up having to do conversions like we saw in the parts by mass. However, you might be lucky enough to get a problem where it's already provided. You just have to know which equation to use. So let's go back to our PowerPoint. And we have mole fraction practice. So mole fraction, a solution of ethanol, which is C2H6O, in water is sometimes used as a disinfectant. 1 liter of this solution contains 553 grams of ethanol, which is C2H6O, and 335 grams of water. What is the mole fraction of ethanol in this solution? So let's go and work it out. So we know that mole fraction is represented with an X, and it's going to be moles of solute divided by moles of solution. All right, so we need to convert both of our solute and our solvent into moles because that's what they need to be in to be plugged in. So that'll be our step one, convert everything to moles. So we have 553 grams of C2H6O. I'm going to set it up on a reaction table to convert from grams to moles. So for every 1 mole, we have 46.068 grams of C2H6O. Our grams will cancel out, and we'll get 12 moles of C2H6O. And because this is what is being dissolved, it is our solute. And now we need to convert our water. So we have 335 grams of water. So for every 1 mole, we have 18.0159 grams. Our grams will cancel out, and we'll have 18.59 moles of water, which is our solvent. And so now we can start to plug it into our equation. So we know that X equals the moles of the solute, which is 12 moles, divided by the moles of the solution. So the solution is going to be the solvent plus the solute added together. So we say 12 plus 18.95. So when you do this math, we say 12 divided by 30.959. And then you can plug that in, and you're going to get 0.392 as our answer. And that's how you solve for a mole fraction type problem. Let's go back to our PowerPoint. And now we're going to start covering the topic of colligative properties. Colligative properties are properties that depend on the number of solute particles. There are 4 types of colligative properties. It's boiling point elevation, freezing point depression, vapor pressure, and osmotic pressure. So each one has its own formula. Boiling point is represented by delta T equals Kb times M times little I. Freezing point is delta T equals negative Kf times M times I. Vapor pressure is P solution equals X solvent times P solvent. Osmotic pressure is pi, which is not the pi from math. It's going to represent osmotic pressure. It's not the 3.14, times MRT times, this is supposed to be a little I. The little I is Van Hoff factor. It's only used in solution where it is an electrolyte solution. This will be explained a little bit later why we only use it in those types of solutions. So now we're going to tell you what each term in those formulas represented. So the capital T is temperature, and this needs to be in Kelvin. So if you're given it in Celsius, make sure you convert before you plug it in. P is pressure. Delta T is change in temperature. So it's going to be your final minus initial. KB is boiling point constant. This is going to vary based off your problem. Your KS is your freezing point constant. This will also vary based off your problem. R is a constant. Make sure you take note of the change in the R value. Before you are using a different R value, make sure you take note that it's 0.0821 ATM times L divided by moles Kelvin. The little m is molality, which we had discussed earlier on. The capital M is molarity. The I is the Van't Hoff factor, and the X is mole fraction. So let's talk about what the Van't Hoff factor is. So like we said, it's represented with the letter I, determined by the number of ions a compound has. So we have a couple examples written below. So we have NaCl. So the Van't Hoff factor is going to be 2 for this because it can be broken up into Na and Cl. So it breaks up into 2 parts. If we look at NgCl2, our Van't Hoff factor is 3. This is because we have 1 Mg and we have 2 Cl ions. So it can break up into 3 different parts. AlCl3, sorry, I made a mistake. It's supposed to be I equals 4. So it breaks up into 4 different components. So ignore the little 3 right there. And then we have Na3PO4. So this one is where a lot of people will mess up. So you have to make sure you pay attention to when you have a polyatomic ion in your compound, because your polyatomic ion won't break up. So your PO4 will stay together. However, your PO4 will act as 1, while your Na, your 3 NAs will act as 3, so you have 4 altogether. The Van't Hoff factor is only determined in electrolyte solutions because non-electrolytes do not break apart, which is why you're only using the I whenever you're dealing with electrolyte solutions. So let me go ahead and go back. So if you're looking at your formulas, when you have a non-electrolyte solution, it'll be exactly the same, however you just take out the I. So that's what's going to be different between the 2 different types of solutions. So now let's move on to an example. It says how many grams of fructose, which is C6H12O5, make sure you're paying attention, it's not fructose, it's fructose, must be dissolved in 419 grams of benzene to raise the boiling point by 3.8 degrees Celsius. The boiling point constant for benzene is 2.67 degrees Celsius divided by M. So let's go ahead and go to our boogie board. So we have delta T equals I times KB M. We know we're using this formula because it mentioned boiling point, that the boiling point was changing. So that's why we're going to use this problem. So what we can do is plug in what we know. So we know that our change in temperature is going to be the 3.8 degrees Celsius. We can leave it in Celsius because the KB number that they provided also had Celsius in the units. However, if you were dealing with a traditional KB, it's generally in it's going to have a unit for Kelvin, and so you would have to convert to Kelvin for that. So we have 3.8 degrees Celsius equals, we were dealing with a sugar, which means it has a I of 1, because just as a reminder, sugars will not break apart either. So because we just have a single sugar, it's going to have a Van 't Hoff factor of 1. Times our Kb, so 2.67 degrees Celsius, and then our M, so molality, which is moles of solute divided by kilograms of solution. So let me write that right up here. Moles divided by kilograms. So we don't know any moles yet because we weren't given anything in moles, but we were given our solution. We weren't given solute, we were given solution, or solvent, sorry. Our solvent was 419 grams. So we need to convert our grams into kilograms to be plugged in to our molality section. So when you convert this, it's going to be 0.419 kilograms. And then we just slowly need to be able to solve for this moles so that we can later convert it into grams. So go ahead and cross out the units that are similar so far. Really, it's just Celsius that can get canceled out. And then we do 3.8 equals 1 times 2. I want to go ahead and convert my little m to kg mole -1, just so that I can end up canceling out another unit. So I'm going to put an x in place of the moles just to signify that that is what I'm solving for. So now that I converted my unit, I can cancel out my kilograms, so I'll just be left with moles once I find out what x is. So if I want to, I can move my 1 over. It doesn't really change much. So I get 3.8 equals, I want to try to get my x value by itself, so I can multiply my 2.67 and my 0.419 to get x by itself. So I say 2.67 times, or sorry, not times, divided by 0.419 x. All I'm really doing is I'm factoring that, like I'm getting rid of that x from the 0.419. And so I can do my math in here, and then I can move that over to the other side of the equation. So 3.8 equals 6.372315 x. Go ahead and put that in parentheses so I know that it's by itself. I can now move my number right here over to the other side by dividing. So we have x equals 0.59633 moles. All right, so now that I have my moles, I can now convert from moles to grams. So I'm going to say 0.59633 moles for every 1 mole. I just look up the periodic table and I find my weight, which is 164.1565 grams. My moles cancel out, and this is, each of these are for the C6H12O5, so that's sugar, equals 97.9 grams of C6H12O5. And that is how many grams I will have. All right. So let's go ahead and go back to our PowerPoint. That was our first example. And now we can move on to another example, which again, we're using a sugar. This one will be dealing with osmotic pressure. So how much glucose, which is C6H12O6 per liter, so grams per liter, should be used for an intravenous solution to match the 7.65 atm at 37 degrees Celsius osmotic pressure of blood. So it's saying that this is the pressure or the osmotic pressure for blood. And we want to know how much glucose we need to match that. So let's go ahead and switch to our boogie board. So we know that I is going to be 1 because we had a sugar. Our T is 37 degrees Celsius, but remember, we need to convert this to Kelvin. So we have 310 Kelvin. They told us, remember, this is not the math pi, it's just representing osmotic pressure. They told us the osmotic pressure is 7.65 atm. And they told us that we have a 1 liter solution. So now let's go ahead and write out what our formula is for osmotic pressure. So osmotic pressure equals I times mRT. We need to find grams, so we can rearrange this formula to be able to find molarity and grams from our molarity. So if we rearrange this equation, we get molarity equals osmotic pressure divided by IRT. And so then we can just simply plug everything in and solve for molarity, because that will give us grams per liter. Which we then can get, or sorry, not grams per liter, moles per liter, where we can convert moles to grams. So big M, we plug in our osmotic pressure, so 7.65 atm divided by 1 times, let me go ahead and box this, times R, which is going to be the 0.08206. I'm going to kind of move downwards. L atm divided by moles per kilogram, and then we have 310 Kelvin, and then we have a temperature of 310 Kelvin. So our Kelvin can get canceled out, our ATM can get canceled out, and that's really all that we can cancel out right now, because we know that our molarity will be in moles per liter. And so now we just need to worry about the numbers itself. So when you plug all of this in, so remember, this is your I. Everything that you plug in here needs to be in a parentheses, because if you just plug it in, it's going to think that you're just dividing by 1. So you need to do 1 times the R value times the temperature, and then do 7.65 divided by that answer. When you do that, you're going to get 0.301 moles per liter. We need to get rid of our liters so that we can get moles by itself. So we'll take account for the 1 liter that they told us we had. So 0.301 moles per liter. And you put the, because they're, you have liters on bottom, you need to put that 1 liter up on top. Liters will cancel out. It's just by 1, so it becomes the same number. So 0.301 moles. And now we need to convert our moles of our sugar into grams of our sugar. So we say 0.301 moles of C6H12O6, and we have, it's about 180 grams per 1 mole of that sugar. So our moles will cancel out and we'll just multiply across, and you will get 54.1 grams of C6H12O6. So that is our answer. All right. Let's go ahead and go back to our PowerPoint, and we can begin to wrap it up. So, brief overview of everything that we covered. We covered the different concentration terms. Remember that the symbols, what each symbol represents. A common mistake is the little m that is for molality. People will mistake it for mass whenever they're reading a problem. So remember that if you're dealing with mass, that it's going to be grams, kilograms, so on and so forth. But if it says that you have little m equals a number, you need to assume that it is molality. If you're ever confused, I highly suggest that you simply raise your hand when you're in an exam and clarify that it is molality and not math. If you ever do get confused for that, you can always ask questions. The second topic that we covered was colligative properties, so boiling point, freezing point, vapor pressure, and osmotic pressure. We worked 2 examples for each of them. However, I do highly suggest possibly going to Khan Academy. So let me go ahead and go to my boogie board so I can write that out for you. So Khan Academy, if you simply go on to Google and you say colligative properties practice, it will plus, or you can say Khan Academy colligative properties, and it can pop up with, I think there's 2 or 3 videos that one gave you basic overview of what colligative properties are, such as what we did today. And then the other one, I believe, works through a couple examples if you need a little bit more practice. Colligative properties are an important concept to know for, I believe it is, it's either on your first or second exam based off what professor you have. So if it is a concept that you're struggling with, make sure that you either view Khan Academy, go to tutoring resources such as supplemental instruction, CASA, your professor's office hours, and get some assistance with the topic. Let me go ahead and end the sharing. All right, well, that is all that we have for today, so best of luck with these topics.